The mixed branch collatz program sits at the intersection of two mathematical worlds. On one side, continuous geometry. On the other, discrete number theory. This piecewise return map tracks a point, y, bouncing between branches, defined by a slope, lambda, and a shift, tau nu. For this proof, we restrict focus to the expanding case, where lambda is strictly greater than 1, dictating the steepness of these branches. As an orbit bounces through this system, it records an infinite itinerary, a sequence of branch choices known as the kneading sequence. Theorem 4.2 makes a precise claim about this sequence. For any non-zero critical orbit in this expanding map, the kneading sequence is never eventually periodic. To prove this, we rely on a proof by contradiction. We will set up a scenario where the continuous geometry of the system is forced to collide head-on with its underlying number theory. In classical dynamical systems, like rational cycle theory or standard beta shifts, mathematicians have a baseline expectation for how these sequences behave. When analyzing standard models, like Perry numbers, it is customary to assume that an orbit's symbolic sequence will eventually fall into a repeating loop. In a symbolic context, we call this being eventually periodic. The orbit goes through an initial transient sequence of branch choices and then settles into a strict, endlessly repeating tail. But the system we are analyzing operates under different rules. We are dealing with varying modulus systems featuring canonical carries. Assuming that a classical, repeating loop can exist in this specific system is exactly the mathematical trap we need to set. We will assume the loop exists and watch the system break itself. Let's formally set up the contradiction. We hypothesize that after n initial steps, the branch code becomes periodic, repeating with a fixed length of r. Algebraically, this means we are taking the return map and applying it r times in a row, iterating over that exact repeating sequence. Because the sequence repeats, the nested affine transformations collapse algebraically into a single r-step map. G of y equals lambda to the r times y plus b. Look closely at the components. The slope is now the original lambda raised to the power of r. Meanwhile, the constant b cleanly absorbs all the specific carry data and local offsets of that repeating period. By assuming symbolic periodicity, we have entirely collapsed the complexity of a chaotic system into a single predictable linear engine, driven almost entirely by that new composite slope. Recall our initial condition. The original slope, lambda, is strictly greater than 1. Raising any number greater than 1 to the power of r creates a much larger number. Therefore, our composite slope is aggressively expanding. This plots the r-step map, g of y, as a steep line intersecting the identity line, y equals x. When an orbit starts anywhere other than this exact intersection, the steep slope repels the iteration violently outward, rapidly escaping the frame. Under a strictly expanding map, all non-fixed points are pushed to infinity. They cannot remain bounded. There is only one way an orbit survives this repeating branch. If the point sits exactly on the intersection of g of y and the identity line, it remains perfectly stationary. Translating this back to the physical system, to remain bounded, the exact coordinate at step n plus r must equal its coordinate at step n. That is the geometric trap. Symbolic periodicity dictates that physical periodicity, a perfectly stationary coordinate, is an absolute, unavoidable requirement. Now, we leave the macroscopic geometry of affine maps and zoom in to the microscopic reality of two-adic arithmetic. This is where Theorem 4.1 comes into play, defining a strict arithmetic invariant that governs non-zero critical orbits. This formula tracks the two-adic valuation of the orbit's denominator at step k. Physically, this means that at every single step k, the orbit's coordinate absorbs a new factor of 2 into its denominator. According to Lemma 1.5, a classical fact about non-cancellation, this newly acquired factor of 2 is exact. It cannot be cancelled out by any subsequent additions in the numerator. Because of this uncancelable addition, the exact reduced fractional value of the coordinate is mathematically forced to change. The denominator strictly grows at every step. Therefore, the exact physical coordinate of the orbit is in a state of permanent, guaranteed change. We now bring the continuous geometry and the discrete arithmetic face to face. On the left, the geometric demand. The orbit must remain perfectly stationary. step n plus r must exactly equal step n. On the right, the arithmetic demand. The physical coordinates denominator is strictly larger at step n plus r than it was at step n. A fraction with a strictly larger reduced denominator can never equal its past self. Since the physical point can never be fixed, a bounded orbit can never exist on a repeating branch. Our initial assumption was false. For expanding mixed return maps, finite symbolic compression is structurally obstructed, and the needing sequence will remain aperiodic forever.